In right triangle trigonometry part 2, we're going to look at some identities and some applications of right triangles. And so the first identities are what we call the fundamental identities, and those involve the reciprocal identities and the quotient identities. And the reciprocal identities you've already looked at when we first defined the 6 trigonometric functions. Because sine and cosecant are reciprocals of each other, that means that sine is 1 over the cosecant and cosecant is 1 over the sine. Cosine and secant are reciprocals of each other, and tan and cotan are reciprocals of each other. And the quotient identities, the tangent is equal to the sine over the cosine, and since the cotan is the reciprocal of tan, cotan is equal to the cosine over the sine. So let's start with an example. All right, here we have example 1. Given that sine of theta equals 2/5 and cosine of theta equals the square root of 21 over 5, find the value of each of the 4 remaining trig functions. I like to write all 6 down and then fill in what we have. So the sine is 2/5, the cosine is the square root of 21 over 5, and now we can evaluate the rest using the identities we've been given. So the quotient identity says that the tangent of theta equals the sine over cosine. So tangent of theta is equal to the sine, which is 2/5, divided by the cosine, which is the square root of 21 over 5. And so if I just take 2/5 and multiply it by 5 over the square root of 21, the 5's cancel. I get 5 over the square root of 21, and we can rationalize that. That would be 5 square roots of 21 over 5. And notice a fast way of doing this, now that when you divide a numerator by a denominator, and they're both fractions, if the denominators are the same, you see they're going to end up canceling out. So you could do that right here and say, oh, that's 2 over the square root of 21. The cosecant is just the reciprocal of the sine, so 5/2. The secant is the reciprocal of cosine, 5 over the square root of 21. Multiplied by the square root of 21 over the square root of 21, we get 5 square roots of 21 over 21. And the cotan, I want to take the reciprocal, but since I'd rather take the reciprocal before I rationalize, so I don't have to rationalize again. So I'll take the reciprocal of the 5 over 21, which would be the square root of 21 over 5. So I'd like you to pause the video, try the next problem, and then start the video up to check your work. Alright, so I'm going to write in the 2 that we have. The sine is equal to 2/3, the cosine is equal to the square root of 5 over 3. The tangent of theta is equal to the sine over the cosine, so it's 2/3 divided by the square root of 5 divided by 3, or 5 over 3. When you multiply by the reciprocal, those are going to cancel, so we get 2 over the square root of 5, or rationalize, that's going to be 2 square roots of 5 over 5. We take the reciprocal of everything. The cosecant of theta is 3/2. The secant of theta is 3 over the square root of 5, or 3 square roots of 5 over 5. Again, if I take the reciprocal of the rationalized tangent, I'm going to have to rationalize again, so I'm going to go back up here, take the reciprocal before I rationalize, so that's going to be the square root of 5 over 2. So in the next part of this video, we're going to be looking at some other identities called cofunction identities. And before we do that, I'd like you to pause the video again, and we'll try to kind of discover what these identities are before you look on the next page. And so you can use your calculator and evaluate these trigonometric functions, and basically look for a pattern across. And once you've evaluated them, on the very last one, I'd like you to evaluate the tangent of 15 on your calculator, but try to guess what the cotan of 75 is before you start the video. Okay, the sine of 30, I already know without using my calculator. The sine of 30 is a half. I know that because of my special triangles, and again, you should have memorized those special triangles by now, but even though in this case I said it's okay to use a calculator, I also know that the cosine of 60 is a half from using my calculator. Alright, let's evaluate the next. We've got the sine of 50. I want to make sure that I am in degree mode, and I am. Sine of 50, close the parentheses, hit enter. And let's do the cosine of 40 and hit enter. So we get the same exact value for the sine of 50 as we did for the cosine of 40, 0.7660. Now let's evaluate the secant of 10 and the cosecant of 80. So to evaluate the secant of 10, I'm going to do 1 divided by the cosine of 10 degrees. And then I'll do the cosecant, which is 1 divided by the sine of 10 degrees. Alright, now let's do the secant of 10 and the cosecant of 80. For the secant of 10, I'll do 1 divided by the cosine of 10 degrees. And then for the cosecant of 80, I'll do 1 divided by the sine of 80 degrees. I get the same exact value, so 1.0154. On the last one, I've got the tangent of 15 degrees and the cotangent of 75. I'm going to do the tangent of 15. Okay, and that's 0.2679. And before I evaluate, I want to look for a pattern, and you should have looked for a pattern. And what we're noticing is that definitely, the values in the first column are the same. So it would be very easy to make a guess on this one just because of the fact that both are the same. But I guess the pattern I'm looking for is what are these angles, what are the pairs of angles have in common? And I hope you notice that they add up to 90 degrees. And so the answer to the cotangent of 75 should be the same as the tangent of 15. 75 and 15 add up to 90 degrees. And I'm wondering if you remember what it means when two angles add up to 90, or what you call them. And they're called complementary angles. The sum is equal to 90 degrees. And then if the sum is 180 degrees, do you remember what you call those angles? And those are called supplementary angles. So what I've done is I've written the 6 trigonometric functions out in a slightly different order than I usually do. Usually I set them up so that the sine and its reciprocal are next to each other, and the cosine and its reciprocal. But these are not reciprocal. The relationship here is not reciprocal. They are complementary. The relationship is not reciprocal. They're actually what we call co-functions. So we've got the sine and its cosine. They are co-functions. Tangent and its cotangent, and secant and its cosecant. And what's happening here is that basically co-functions of complementary angles are equal. Alright, so if co-functions of complementary angles are equal, let's look and see what that looks like as an identity. So we'll slide to the next page. These are called co-function identities. It says the value of a trigonometric function of theta is equal to the co-function of the complement of theta. And so basically what that means is if you have the sine of theta, that's equal to the cosine of 90 minus theta. The tan of theta equals the cotan of 90 minus theta, and the secant of theta is equal to cosine of 90 minus theta. Now you can change, and this works both ways, and you can also change theta to radians by replacing the 90 with pi over 2. So what I'd like you to do is pause the video and try the few practice problems, and then start the video up and check your work. All right, let's look at number 1. We know the cosine of 20 is going to equal the sine of 90 minus 20 degrees. So that would be the sine of 70 degrees, as long as these add up to 90. The tan of 5 is going to equal the cotan of 90 minus 5 degrees. So that would be the cotan of 85. The secant of pi over 3 will equal the cosecant of pi over 2 minus pi over 3. So we'd have to get a common denominator of 6, so that would be 3 pi over 6 minus 2 pi over 6, which is pi over 6. The sine of 40 is going to equal the cosine of 50. Cosecant of 80 is going to equal the secant of 10. And since pi over 2 plus pi over 2 add up to 90, the cotan of pi over 2 equals the tan of pi over 2. Right, so that's it for the cofunction identities. They're fairly reasonable and simple to use. All right, in the next video we're going to derive what we call the Pythagorean identities, and those are based on the Pythagorean theorem.